To name this first compound, we want to find the longest parent chain. And you can try circling different things here. If I did this one, my parent would be 1, 2, 3, 4, 5, 6, 7, 8, which would be octane. But if I did this, that would be nonane. So I'm going to erase this blue one here. You could try doing this here, and that would give you 10. So we're just going to rule out the red version there. So that one is 10 carbons long. And so my parent name will be decane. And now I go to look for the substituents off of here. And this has 4 carbons and it's attached at the second carbon. So this is a sec-butyl. This has 2 carbons. This is an ethyl. And this is a methyl. And when I go to number them, I want the lowest overall numbering. In this direction, it gives me methyl at 2. And so I have a methyl at 2, ethyl is at 4, and my sec-butyl is at 5, and now I just put them in alphabetical order. So we're going to go off of the B of butyl here. So this will be 5 sec-butyl, 4 ethyl, 2 methyl, decane. In the next example, again, you're going to find the longest carbon chain, which looks like it might be this one. That's another 10 carbon. We can also do a 10 carbon in this direction here. In the red version, we have the more substituents in terms of more complex substituents. So that's the one that we are going for here. So we're going to number it using the red. And we have a methyl. There's 2 of those. This one over here has that Y shape. There's 3 carbons. This is an isopropyl. And this one is an ethyl. I'm going to number in this direction to give us the lowest numbering. And the one that comes first in the alphabet will be ethyl. So it would be 3 ethyl. Be 6 isopropyl. And isopropyl is one of the exceptions where the I is used for the alphabet instead of the M. And I have 2 methyl groups at 2 and 4 dimethyl decane. For question 17, we need to identify whether the compounds are constitutional isomers or different representations of the same compound. So one method is to try to flip it in your head, or you can also use the models. So what you're seeing is the first structure there that has the 1, 2, 3, 4, 5 carbons. And then there's 2 methyl groups coming off of the second carbon. And if I try to rotate this compound, I'm going to see if I can actually get to that structure, the second structure. So I'm trying to find a way to rotate it so that my carbons match that. And there's actually not a way to do that where both of the carbons are in that manner. The only way that I can do that is to take carbons off and reattach them onto a different carbon, which makes it a different compound. So this would be the structure that you would see on the page there, where there's the 5 carbons and then these 2 methyl groups on that third carbon. So these are constitutional isomers. The second way to identify if things are the same or are constitutional isomers is to name them. My long chain here is pentane. I have 2 methyl groups at the front end, so 2, 2, dimethyl, pentane. And if I go to name the second one, this is still the same parent. but my methyls are now at 3. If they have different names, they are different compounds. In letter C, this is the structure here that has the carbon chain going across. Might be in a slightly different rotation here. So then we can see all these carbons going across. We have the isopropyl group and the methyl group sticking up off of there. And then you can try to rotate this around or flip it over to get it to look the same as in the picture. So I'm going to try to do that here. On the right side, this is the carbon methyl. So there's the isopropyl group that's coming off of here. This carbon chain here with the methyl going down. And then this is the rest of the molecule. So this letter C is different representations of the same compound. In this case, the formula is the same, so they are constitutional isomers. If I go now to name the second one here, this is my long carbon chain. I have 2 methyl groups and an ethyl, so this one is 3-ethyl. 2,4-dimethyl. Heptane. This one is 2,4-dimethyl. My ethyl is first at 3, and heptane. So these are same. This one is a constitutional isomer. In this question, we're drawing the compounds. And I always start with the parent name. So to draw 2,2,4-trimethylpentane, I have a 5-carbon chain. At 2 and 2, I have a methyl, 2 methyls, and 4, there's a methyl. So that is what that one would look like. For tetramethylcycloheptane, I have a 7-membered ring. So the heptane tells us 7, cyclo is cyclic. So I have cycloheptane. At 1, I have methyl. 2, there's a methyl. 3, there's a methyl. And 4, there's a methyl. So tetramethylcycloheptane. Here we're looking to draw the most stable Newman projection of 3-methylpentane. So we first want to draw 3-methylpentane. That's pentane with a methyl group. We're looking down the C2-C3 bond. What you're looking at here is the structure of 3-methyl. So there's our methyl group and pentane. So I have a 5-carbon chain here. And we're going to look down this bond right here, the 2,3 bond. And I want to look for the most stable conformation, which means that here is my front carbon. On that front carbon, I have 2 hydrogens, which I've shown in yellow just so that you can see there, and a methyl group. And then on the back carbon, I have this ethyl group. This bond between C2 and C3 we can't see. From the side, you can see C2 to C3, but from the front, we don't see the C2 to C3. So we have this ethyl group. There's a methyl group coming off to the side and the H there. If we're looking for the most stable, the large groups on each carbon should be away from each other as far as possible. So on this one right here is my back carbon large group, which is the ethyl, and on the front this is the methyl, and this is how it would be when it's as far apart as possible. If I were to rotate to this would be the eclipsed version, and that would be the highest in energy and the least stable. So we want the one that is lowest in energy, which is the most stable. So that is what that one will look like. We have the 2 hydrogens sticking up, a methyl sticking down, and then the methyl to the side. On the back carbon, a hydrogen out to the side, this ethyl group up here. So on the front carbon, we had the H's to the side. There was a CH3 pointing down. And on the back carbon, I had the ethyl group that was away from the CH3. There was a CH3 off to the side, and then we have the H over here. So this is the most stable conformation. It is lowest in energy, and it is referred to as the anti-staggered conformation. Here is another one where we're going to draw a Newman projection, and it is helpful to have the model of this one, which I will show you right now. This is the structure that you're seeing on the page. I have my 4-carbon butane chain. The chlorines are coming out at you, so you can see they're coming towards you here, and the bromines are pointed away from you. So in this situation, the direction that our chlorines and bromines are pointed in our Newman projection are going to be important because they've designated the wedges and the dashes specifically. Here we're looking to draw any projection. We can start with the anti-staggered. If I'm looking at the front carbon, this is my carbon. I have the CH3, the bromine, and the chlorine. And if I want everything in the anti-staggered, my bromines should be as far away from each other as possible. I know it doesn't look like it is the biggest group here, but bromine is much larger than chlorine, so the bromines should be on opposite sides of each other. So if I draw the Newman projection for the front carbon, I have this carbon, the CH3 is off to the side, I have the chlorine and the bromine pointing down, and on my back carbon is the wheel. I have the bromine sticking straight up, so you can see that sticking straight up in the back. Opposite the other bromine, there's a CH3 to the side, and the chlorine is off to the side. So this would be an anti-staggered conformation. So if you look at your structures here like they're in a clock, the chlorine is just to the left of the methyl group, which then goes to the bromine if you're going in the clockwise direction. So you shouldn't have your compounds going chlorine, bromine, methyl. It should be chlorine, methyl, and then bromine. Now we can do a different conformation. So let's say I want my methyl groups to be opposite each other. This would be a gauche conformation. So I have my front carbon, there's a methyl group, bromine to the side, chlorine. On the back carbon, I have a bromine off to the side up here. So that's this one right there. Then there's the CH3 sticking down, and then I have the chlorine off into the side here. This is a gauche, which is a form of a staggered conformation, but it's not the anti-staggered. While you go to the gauche, you usually encounter an eclipse. So this would be one form of an eclipse version, where these groups are covering each other. And you can draw that one. And the full eclipse would be where the largest groups, which are the 2 bromines, are covering each other. So this would be the full eclipse. And to draw that one, I have my bromine to the side, chlorine, methyl, and on the back wheel my bromine is eclipsing this other one. Then I have the methyl and a chlorine over here. So this would be the full eclipse. And that one is highest in energy. To rank these conformations in order of increasing energy, the one that is highest energy, which is the least stable, will be the full eclipse. So if I was going to rank them 4, and the full eclipse will be where the 2 biggest groups, which are the bromines, are blocking each other. So this will be the highest in energy. This is the next eclipse one, so this would be 3. And between my 2 staggered, I have the gauche, in which the bromines are staggered from each other, but they're not directly across from each other. This one is the anti. This is the lowest in energy, and that one comes next. Okay, here we're looking to draw chair conformations of each of the following compounds and identifying the more stable chair conformation. The first thing that we want to do is draw out the structure of trans 1,2-diisopropyl cyclohexane. At 1 and 2, I have an isopropyl group. One of them is going to be pointing up, the other is pointing down, which I have built here. So at one position, my isopropyl group is pointing up. and the other one is pointing down, which makes it the trans. So you can kind of see the chair structure here. And all of these are in the axial position the way that I have them built here. And you can see that I also have axial hydrogens that are pointing down, and these hydrogens here are axial up on every other carbon. So now I can draw the chair. So we want to number these. I number my carbon starting here, and my isopropyl group here is axial up. It's sticking straight up and down, and that's where the corner is. At 2, the corner is pointing down, so that's indicating the direction of my axial group, which is sticking straight down here. So that one has both groups in the axial position. And if you wanted to fill in the hydrogens, you could. So this is carbon 2. At 3 or at 4, the hydrogen is axial down. And at 6 over here, the hydrogen is down. So if you drew a different chair in a different direction, so if it was leaning or slanted a different direction, then your chair might look a little bit different. So when we do the chair flip, you can see before we do the chair flip here, my isopropyl groups are axial, sticking straight up and down, as are the colored hydrogens. So I'm going to do a chair flip, and I'm going to flip this down and flip that other side up. So you're going to see me flip this side down, and I'm going to flip this up, and when I do that now, you should be able to see that my chair has slanted in a different direction. So now it's slanting in a different direction, and all of my groups have shifted from being axial. Now they're all equatorial. My isopropyl group at carbon 1 is still up. This one is still pointing down, but it's just gone from axial to equatorial. So even though they were trans before, it's still trans, but the trans is referring to the direction that the groups are pointing, not whether it's both axial or both equatorial. Because now they're both equatorial. One is equatorial up, 2 is equatorial down. And all of the hydrogens that were down before, the orange ones were down, they're still pointing in the down direction. The hydrogens that were up, the yellow ones, are still up, but everything before that was axial is now equatorial. The more stable chair conformation is going to be the one where the largest groups are in the equatorial position. So that will be this second chair that I've drawn. So it doesn't matter where you started your numbering. So I'm going to flip it back once, so you can see my axial group. So let's say that you drew your structure and you started your one at this position here, and this would be over here. One is still up, one is down. You still have the chair. This one is now up equatorial, this is down equatorial. So it just really depends on where you start your numbering and where you put your things on the ring. But relative to each other, they're still up, one is down, and in this case these are equatorial. Once you do the chair flip, those become axial. So same question, different compound. Now we're dealing with cis cyclohexane. So my isopropyl groups should both be up, or they can both be down. So it doesn't matter if they're both up or down, as long as relative to each other they're the same direction. So I go to draw my chair. This is 1 and 2. They're both going to be pointing up. If this is 1, this is 2. My corner here is 1, so that tells me that my axial group is up. In this case, isopropyl is up, so that will be up axial. And then at 2, my corner is pointing down, so that means I have an axial group that's down. and my down group here is the hydrogen. So my isopropyl will be equatorial here. I'm going to do my chair flip. Everything will slant the other way. And this is now 1, this is 2. The isopropyl group is still pointing up, but my corner points down, so the hydrogen is down here. This is up, and then this becomes axial up. So this is now equatorial, axial. So the axial is like the axes on the Earth, it goes up and down. Equatorial is like the equator, it kind of goes out to the side. In this case, I have one group that is axial, one equatorial. In the second case, after the chair flip, I have axial and equatorial. So these have the same stability. Or tied. All right, for each of these, determine which compound is more stable. You may find it helpful to draw out the chair. You can't just base stability on how many groups are on the ring or whether they're up or down. You have to actually draw the chairs out. So if I draw the first one, at 1, this group is down. 2 is going to be up. 3 is down. So in this situation, all of these groups are equatorial. So that's the first chair. If I draw the second structure, this one is down, 2 will be down, 3 is up. So here all of these are equatorial, which is the most stable. So all three are equatorial. And this one I have 2 axial, 1 equatorial. But you also want to consider that when you do the chair flip, those axials are going to become equatorial. So now I have 2 equatorial, 1 axial. And that is going to be more stable than the initial. So you always have the possibility of that other chair conformation. Just like you do with the first one, you have the possibility of all 3 being axial. But we know that they can flip back and forth and stay in the more stable compound. So it's better to have all 3 groups equatorial than it is to have 2 versus 1. So the most stable one is going to be the first structure there. For this one here, it's the same exercise. You want to find out which chair is going to give you the most stable, the one that has the more equatorial groups. So at 1 that is down will be equatorial, 2 is equatorial up, 4 is equatorial up, 5 is equatorial down. That one is all equatorial. So 1 is up, 2 is down, 4 is up, 5 is down. So here I have 2 axial, 2 equatorial, and if I do the chair flip, I'm also going to still get 2 axial, 2 equatorial. So in the scenario where we have all 4 things equatorial, that will be the most stable.